an application for systems. In the previous lecture, we examined an application for systems of linear equations with 4 or more variables that involve the calculation of traffic flow through a network of streets. In this lecture, we will examine another type of application that can be solved using systems of linear equations with 4 or more variables, called curve fitting, which is the process of finding a mathematical function whose graph fits a given set of data points. Given a group of points, we will try to find a curve whose graph passes through those points. In these examples, we will use a curve described by the function ax cubed plus bx squared plus cx plus d, where a, b, c, and d are constants which determine the exact shape and position of the curve. An equation of this form is called a cubic or third-degree polynomial equation, since the highest power to which x is raised is 3. In the real world, an equation like this might describe some sort of physical system. The quantities x and y could represent the relationship between any two measurable quantities of the system, such as the temperature versus pressure in an engine cylinder, or the number of gazelles in a wildlife preserve versus the number of lions, or the amount of money invested in the stock market versus the amount of coffee drunk by investors. So let's say that 4 measurements are taken of a system described by a third-degree polynomial function. Given the x and y coordinates of these 4 data points, x is raised is 3. In the real world, an equation like this might describe some sort of physical system. The quantities x and y could represent the relationship between any two measurable quantities of the system, such as the temperature versus pressure in an engine cylinder, gazelles in a wildlife preserve versus the number of lions, of a system described by a third-degree polynomial function. Given the x and y coordinates of these 4 data points, how can we find the values of the 4 constants a, b, c, and d, which determine the shape of the curve that passes through those points? In this problem, we have an equation with 4 unknowns a, b, c, and d. We also have 4 different sets of values for x and y which we know satisfy that equation. If we substitute these values for x and y into the equation, we can create 4 different valid equations where the unknowns are a, b, c, and d. We then rearrange and simplify the equations so that they are in better form to solve the system using Gauss-Jordan elimination. Equations into matrix form and reduce the matrix using Gauss-Jordan elimination. We start by changing the first row's leading entry to a positive 1. We will do this using a swap operation to exchange rows 1 and 2. We then change the entry below that to a 0, using a pivot to add 1 times row 1 to row 2. The entry below that is then zeroed, using another pivot to add -8 times row 1 to row 3. And we zero the entry below that, using a pivot to add -27 times row 1 to row 4. We now move to the second column, changing row 2's leading entry to a 1, using a scale operation to multiply row 2 by 1/2. We then change the entry below that to a 0, using a pivot to add 4 times row 2 to row 3. The entry below that is then zeroed, using another pivot to add 18 times row 2 to row 4. Now we move to the third column, changing row 3's leading entry to a 1, using a scale operation to multiply row 3 by -1/6. The entry below that is then zeroed, using a pivot to add 24 times row 3 to row 4. Moving to the fourth column, we change row 4's leading entry to a 1, using a scale operation to multiply row 4 by 1/4. Now the leading entry of every row is a 1, and the entries below these leading entries are zeros, as required for reduced row echelon form. However, to be in reduced row echelon form, every entry above each leading entry must also be 0. We start by zeroing all the entries above the leading entry of the fourth row, starting with the entry directly above that leading entry. Using a pivot, we add -1/2 times row 4 to row 3. Next, we zero the entry above that, using a pivot to add -1 times row 4 to row 2. And finally, we zero the top entry in that column, using a pivot to add -1 times row 4 to row 1. Since all entries above the fourth row's leading entry are now 0, we move to the leading entry of the third row and zero the only non-zero entry above it. Once again, we use a pivot, adding -1 times row 3 to row 1. Since all the entries above the third row's leading entry are now 0, we move to the leading entry of the second row and zero the entry above it, using a pivot to add -1 times row 2 to row 1. The matrix is now in reduced row echelon form. As we saw in the chapter on parametric equations with Gauss-Jordan elimination, since every column to the left of the vertical line contains a leading entry, and is therefore a pivot column, the system has a single unique solution. Converting the matrix back into equations, we see that the values of A, B, C, and D are 1, -3, -1, and 4, giving us the values of the 4 coefficients in our third-degree polynomial function. Knowing these coefficient values, we can now graph the function, either by plugging in various values for x and calculating the corresponding y values, or by using a graphing calculator. Since these coefficient values were the single unique solution for the system, we know that this is the only third-degree polynomial function that passes through these 4 points. But we have seen that sometimes systems of equations can be inconsistent, having no solutions. To see how this can happen, let's take the same 4 points as before and move one point so that it is positioned directly under one of the other points. Now we have a configuration where 2 of the points have the same x-coordinate. To solve for A, B, C, and D, we once again substitute the values of x and y from each of the 4 points into our equation, giving us a system of 4 equations in 4 unknowns. We then rearrange and simplify the equations. We once again start by changing the first row's leading entry to a +1, using a swap operation to exchange rows 1 and 2. We then change the entry below the first row's leading entry to a 0, using a pivot to add 1 times row 1 to row 2. The entry below that is then zeroed, using another pivot to add -1 times row 1 to row 3. But this has produced a matrix row containing all 0 coefficient entries with a non-zero constant entry, indicating an inconsistent system. Since inconsistent systems have no solutions, this tells us that there are no values for the coefficients of this function that are consistent with these 4 data points. In fact, it is impossible for any curve that passes through these 4 points to be a function of x, since that curve would not pass the vertical line test for a function. So far, we have seen that when curve fitting a polynomial equation to data points, the system of linear equations generated by this problem can have no solutions, or a single unique solution. But is it possible for the system to have infinitely many solutions? Let's see what happens when we are given only 3 points. Once again, we start by substituting the known values of x and y into our function. The equations in 4 unknowns A, B, C, and D. And just as before, we rearrange and simplify the equations. We now write the system of equations in matrix form and reduce the matrix using Gauss-Jordan elimination. We start by changing the first row's leading entry to a positive 1, using a swap operation to exchange rows 1 and 2. We then change the entry below that to a 0, using a pivot to add 1 times row 1 to row 2. The entry below that is then zeroed, using another pivot to add negative 8 times row 1 to row 3. Now we move to the second column, changing row 2's leading entry to a 1, using a scale operation to multiply row 2 by 1/2. We then change the entry below that to a 0, using a pivot to add 4 times row 2 to row 3. Now we move to the third column, changing row 3's leading entry to a 1, using a scale to multiply row 3 by negative 1/6. Now the leading entry of every row is a 1. In reduced row echelon form, all the other entries in every column containing a leading entry must also be 0. We start by zeroing the only non-zero entry above the leading entry of the third row, using a pivot to add negative 1 times row 3 to row 1. We then zero the entry above the second row's leading entry, using a pivot to add negative 1 times row 2 to row 1. The matrix is now in reduced row ends with Gauss-Jordan elimination, since only 3 of the 4 columns to the left of the vertical line contain a leading entry. There are only 3 pivot columns. And so we know that the system has infinitely many solutions. And as we saw in that lecture, when writing parametric equations for these solutions, the unknowns associated with the pivot columns are treated as dependent variables, and the unknown associated with the remaining column is considered to be a free variable. To create the parametric description of the solution set, we first convert the matrix rows into equations, and then rearrange the equations so that the dependent variables are alone on the left side. This gives us equations that express the dependent variables a, b, and c as functions of the free variable d. We then equate the free variable d to a parameter that we will call t, and then replace d in the remaining equations with the parameter t. This gives us a set of parametric equations that express a, b, c, and d as functions of a single parameter t. Any value we pick for the parameter t will produce values for the coefficients a, b, c, and d in our polynomial function that will cause its graph to pass through the 3 given data points. For example, if we choose a value of 4 for t, our parametric equations produce values of 1, -3, -1, and 4 for a, b, c, and d. Or if we choose a value of 2 for t, our parametric equations produce values of 0, -1, 0, and 2. Or choosing a value of 0 for t gives us values of -1, 1, Although these three functions and graphs are very different, each curve includes the three given points. In fact, any one of an infinite number of possible values for t will produce a unique third-degree polynomial function and graph that includes these 3 points. So far in these lectures, we have studied different applications of linear functions and have seen that these functions are graphically represented by straight lines or surfaces. In the next lecture, we will introduce quadratic functions whose graphs are parabolas.